my previous session, I have dealt with image enhancement techniques where a single image has been manipulated so that the visual appearance of the image improves. In this session, I now deal with image transformations where by applying some mathematical operators or functions, the image is manipulated to generate a new image to yield some specific characteristics of the image. Image transformations will be dealt in two sessions. In the first session, simple transformations will be discussed, while in the next session, orthogonal transformations and some special indices would be discussed. Image transformations involve the manipulation of multiple bands of data, whether from a single multispectral image or from two or more images of the same area acquired at different times, that is multi-temporal image data. Either way, image transformations generate new images from two or more sources which tend to highlight a particular feature or properties of interest better than the original input images. The basic image transformations use arithmetic operators such as addition, subtraction, division and multiplication. So, now let us look at these basic arithmetic operators one by one. Image subtraction. In image subtraction, two geometrically registered images acquired at two different dates are subtracted pixel by pixel to yield a new image called the difference image. In these new images, areas where there are little or no changes are represented in mid-gray tones, while those areas where significant change has taken place and are shown brighter or darker tones depending on the direction of change in the reflectance between the two images. This type of image transformation can be useful for mapping growth of cities, deforestation, crop acreage, etc. Hence, image subtraction is also known as change detection. Let us now look at image addition. Image addition is basically an averaging operation in order to reduce the overall effect of the noise. It is very commonly used in spatial filtering to enhance features. Image multiplication of two real images is rarely performed in remote sensing. The next basic arithmetic operator is image division. Image division or spectral ratioing is one of the most common transformations applied to image data. It serves to highlight subtle variations in the spectral response of various surface covers. By ratioing the data from two different spectral bands yields useful information regarding the objects. Healthy and green vegetation reflects strongly in the near infrared portion of the spectrum, while absorbs strongly in the visible red. Other types of surface such as soil and water show nearly equal reflectance in both the near infrared and red portions. In this particular slide, the basic concept of the different broad categories of land use or land cover are shown, and what we can see is that when we look at water in the near infrared region, it has a very low response, while in the red band again it has a low response, and thereby when we undertake the process of division, the value is close to 1. Similarly, for soil in the near infrared region, the reflectance is high, while in the red region also the reflectance is high. Again, when we take the division of these two bands, the value is close to 1. But in case of vegetation, what we find is in the near infrared region, the spectral response is very high, while it is low in the red. Thus, when we take the division of the near infrared information to the red information, what it yields is a very high ratio value, and this is what actually we are interested to emphasize through the process of vegetation indices. Thus, when we look at a ratio image of a near infrared band, that is between 0.8 to 1.1 mu meters, divided by the visible red band, which is between the region of 0.6 to 0.7 mu meters, it would result in ratios which are much greater than 1.0 for vegetation and ratios which are around 1 for soil and water. Hence, the discrimination of vegetation from other surface cover types is significantly enhanced. This ratio is commonly known as vegetation indices, or in short called as VI. Another advantage of ratioing is that it yields relative values instead of absolute brightness values, hence variation in scene illumination, which as a result of topographic effects are reduced. In this particular slide, we try to look at the problem of varying illumination, specifically in the mountainous regions, wherein one side of the mountain slope may be subjected to the illumination from the sun, while the other is blackened out or it is in the shadow portion. Now, what happens is that the same ground cover type will now have different DN values or brightness values. For example, the vegetation on the higher elevation of the mountain face in this particular slide, which is illuminated, the brightness value is 54, whereas in the shadow it is 39. Thus, it could be interpreted that they are in the raw data, it is two different types of information. Similarly, for the other type of information, we find that on the illuminated slope the value is 62, whereas it is 43 in the shadow portion. When we look at the same phenomena in the second band, again we find the same type of phenomena exist, that is, in the shadow portion the same ground cover, the value decreases significantly, which means that due to the topography there has been a effect on the brightness values of the same ground cover. By undertaking the process of division or ratioing, what we find is that this variation in the brightness is now normalized, or we can say it is removed. So, what we find is that now the values for the two cover types which are shown in this particular slide, the values are consistently or more or less equal to each other, and thereby we now have similar brightness values for the same ground cover. Vegetation indices. Analysis of vegetation and detection of changes in vegetation patterns are key to natural resource assessment and monitoring. Thus, the detection and quantitative assessment of vegetation is one of the major applications of remote sensing for environmental resource management and decision making. Healthy canopies of green vegetation have a very distinct interaction with energy in the visible and near infrared regions of the electromagnetic spectrum. In the visible region, plant pigments, notably chlorophyll, causes strong absorption of energy, primarily for the purpose of photosynthesis. This absorption peaks in the red and blue areas of the visible spectrum, thus leading to the characteristic green appearance of most leaves. In the near infrared, however, a very different interaction occurs. In this region, infrared energy is strongly scattered by the internal structure of moist leaves, leading to a very high apparent reflectance. It is this strong contrast between the amount of reflected energy in the red and near infrared regions of the electromagnetic spectrum that has prompted number of attempts to develop quantitative indices of vegetation condition using remotely sensed images. Since 1960s, scientists have extracted and modeled various vegetation biophysical variables using remote sensing data. Lot of research has been undertaken to develop vegetation indices. Well, vegetation indices can be defined as a dimensionless radiometric measure and is a indicator of relative abundance and activity of green vegetation. It often includes leaf area index or LAI, percentage of green cover, chlorophyll content, green biomass and absorbed photosynthetically active radiation, in short APAR. A vegetation index to a large extent should be able to maximize the sensitivity to plant biophysical parameters having a simple relationship such as linear in nature, so that it is applicable for a wide range of vegetation conditions and to facilitate ease in validation and calibration of the index. Normalize or model external effects such as sun angle, viewing angle and the atmosphere for consistent spatial and temporal conditions. Vegetation indices tend to normalize the internal effects such as canopy background variations, include topography such as slope and aspect, soil variations and differences in senescence or woody vegetation. It can be correlated to some specific measurable biophysical parameter such as biomass, LAI or APAR as part of the validation effort and quality control. The proposed VIs are applicable to both low and high spatial resolution satellite images such as NOAA AVHRR, Landsat TM and MSS, SPOT HRV/XS and any other similar to these that sense in the red and near infrared regions. These have been used in a variety of contexts to assess green biomass and have always been used as a proxy in the context of overall environmental change, specifically in the context of drought and land degradation risk assessment. As a consequence, special interest have been focused on the assessment of green biomass in arid environments where soil background becomes a significant component of the signal that has been detected. Now, let us look at the classification of the vegetation indices. Jackson and Hewitt in 1991 classified vegetation indices into two broad categories or groups: slope based and distance based. To understand this distinction, let us consider the position of vegetation pixels in a plot of red versus infrared reflectance. So, in this particular slide, we can see that in a slope based vegetation indices, lines of equal vegetation slopes represented through NDVI are shown, varying from minus 0.75 to plus 0.75. Where NDVI is equal to 0, this is the line which is probably at equal angular relationship with both the axes. In the second method, which is distance based, the soil line is taken as the major information, and against this the vegetation information is worked out. If the point lies below the soil line, that is towards the infrared region, greater the distance, it is an indicator of greater vegetation information. Closer to the soil line is an indication to the bareness of the ground point in terms of vegetation cover. Another important aspect to be understood here is the position or the projection of the point on the soil line. If the projection is close to the origin of the axis that has been defined, then we say that the soil is having moisture or it is moist soil. Whereas, if it is towards the higher end of the soil line, it is an indication of the dryness of the soil and the cover of vegetation being greater at this particular location. The slope based vegetation indices are simple arithmetic combinations that consider the spectral response patterns of vegetative areas in the red and near infrared portions of the electromagnetic spectrum. Thus, the index can be produced by a set of corresponding red by infrared reflectance values that form a line emanating from the origin of a 2D plot. Different levels of index can be envisaged as producing a spectrum of such lines such that they differ in their slope. The distance based vegetation indices measure the degree of vegetation present by evaluating the difference of pixel reflectance from the reflectance of the bare soil. A key concept here is that a plot of the positions of the bare soil pixels of varying moisture levels in a 2D plot will tend to form a line known as the soil line. As vegetation canopy cover increases, the soil background becomes progressively obscured, with vegetation pixels showing a tendency towards increasing perpendicular distance from this soil line. All indices in this group, such as the perpendicular vegetation indices or PVI, require the slope and the intercept of the soil line to be defined by the image being analyzed. To these two groups of vegetation indices, a third group can be added called as the orthogonal transformation vegetation indices. Orthogonal indices undertake a transformation of the available spectral bands to form a new set of uncorrelated bands within which a green vegetation index band can be defined. The tassel cap transformation is perhaps the most well known in this particular group. So, now let us look at the different types of slope based vegetation indices. As I have said, slope based vegetation indices are combinations of the visible red and the near infrared bands and are widely used to generate vegetation indices. The values indicate both the status and the abundance of green vegetation cover and biomass. Some of the important slope based vegetation indices are ratio, NDVI, RVI, NRVI, TVI, CTVI and TTVI. So, now let us look at each of these commonly slope based vegetation indices. First is the ratio vegetation indices, or commonly known as ratio or simple ratio, and was first proposed by Birth and McVie in 1968 to separate green vegetation from soil background using Landsat MSS imagery. The ratio vegetation index is produced by simply dividing the reflectance values in the near infrared band and the red band. Below is the representation of the same in mathematical form, where ratio is equal to the ratio of the n of the spectral reflectance in the near infrared to the spectral reflectance in the red band of the electromagnetic spectrum. This vegetation is clearly able to capture the contrast between the red and the infrared bands for vegetated pixels, with high index values being produced by combinations of low band due to absorption of chlorophyll and high infrared as a result of leaf structure reflectance. Further, this index eliminates the problem of variable illumination as the effect of topography is minimized. However, this indices is susceptible to division by zero errors and the resulting measurement scale is not linear. As a result, ratio vegetation indices image do not have normal distributions, making it difficult to apply for some statistical procedures. Here we can see the ratio image of a particular area. The bright portions in the image show the vegetation content being much greater than to those informations such as water bodies and river courses, which are having low reflectance and they are depicted in white. So, by undertaking the process of ratioing, we have now been able to segregate the healthy vegetation from all other information as it is being depicted in the bright tone in the image. The next ratio, slope based ratio indices, is the normalized difference vegetation indices, or commonly known as NDVI. Normalized difference vegetation indices was first introduced by Rouse et al. In 1974 in order to produce a spectral vegetation indices that separates green vegetation from its background soil brightness using Landsat MSS digital data. It is expressed as the difference between the near infrared and the red bands normalized by the sum of the near infrared and the red bands. This is one of the commonly used vegetation indices as it retains the ability to minimize topographic effects while producing a linear measurement scale. In addition, divisions by zero errors are significantly reduced. Furthermore, the measurement scale has a desirable property of ranging from -1 to +1, with 0 representing approximate value of no vegetation and negative values representing non-vegetative surfaces. This particular image shows the NDVI image, which has been generated by taking the NDVI of the near infrared and the red band of data. This image is very similar to what we have seen for ratio. However, what we can find here is that the different densities of forest covers are more explicitly shown in this particular image. The next indices is the transformed vegetation indices, or what we call it as TVI. Transformed vegetation index is a modified version of NDVI, which was introduced by Deering and et al. In 1975, where a constant value of 0.5 is added to all the values of NDVI and the square root of the same is taken. The constant of 0.5 has been introduced in order to avoid operating with negative NDVI values. The calculation of the square root is intended to correct the NDVI values that approximate a Poisson distribution and introduce a normal distribution pattern. With these two elements, the TVI takes the form as shown here, where TVI is nothing but it is the square root of the NDVI plus 0.05. However, the use of TVI requires that the minimum input of NDVI values be greater than -0.5 to avoid the termination of the operation due to zero divide. Negative values will still remain if the values are less than -0.5 found in the NDVI. Moreover, there is no technical difference between NDVI and TVI in terms of image output or active vegetation detection. This particular slide shows the TVI information which has been extracted, and what we can see is that denser forest areas are appearing in black color, while the soil information or exposed soils are being shown in bright spots. Further, all water bodies are appearing in black color. Along with this, we have the histogram, which shows the spread of the information of the new image which has been created. What we find is that the majority of the information is concentrated towards the lower end of the histogram which has been shown. The next indices is the corrected transformed vegetation indices, or CTVI. Well, this indices has been introduced by Perry and Lautenschlager in 1984 and aims in correcting the TVI. It was observed that by simple adding or a constant of 0.5 to all NDVI values does not always eliminate all negative values, as NDVI values may range from -1 to +1. Values that are lower than 0.5 will leave a small negative values after the addition operation. Thus, CTVI is intended to resolve this situation by dividing NDVI plus 0.5 by its absolute value and multiplying the result by the square root of the absolute value. This suppresses the negative NDVI, and equation of the same can be written as shown below. CTVI is nothing but the ratio of NDVI plus 0.05 divided by the absolute value of NDVI plus 0.5 multiplied by the square root of the same. Given that the corrections is applied in a uniform manner, the output image using CTVI should have no difference with the initial NDVI image or the TVI. Whenever CTVI properly carries out the square root operation, the negative correction is intended to eliminate negative values and to generate a vegetation in this image that is similar to, if not better than, the NDVI. This image shows the CTVI image which has been generated. The information representation is very similar to what we have seen for NDVI or TVI or for ratio, except that what we find is that the representation of the histogram in this particular case has widened significantly and thereby providing density informations regarding the vegetal cover. The next indices is what we call it as the Thiams transformed vegetation indices, or in short TTVI. Thiams in 1997 indicated that the resulting image of CTVI are very noisy due to an overestimation of the greenness. He suggested that ignoring the first term of the CTVI equation in order to obtain better results. This is done by simply taking the square root of the absolute value of NDVI in the original TVI expression to give a new vegetation indices called Thiams transformation vegetation indices, or TTVI. So, TTVI can be expressed as the square root of the absolute value of NDVI plus 0.05. This particular slide shows the TVI image that has been generated. Again, what we can say is that this particular information is more or less similar to what we have seen in previous indices, which was CTVI. The next indices that we now take up is the ratio vegetation indices. Well, it has been observed that the ratio vegetation indices, which was suggested by Richardson and Wiegand in 1977 as graphically having the same strengths and weaknesses as the TVI while being computationally simpler. RVI is clearly the reverse of the standard simple ratio, that is ratio as shown by this particular expression. Here, when we look at the RVI image which is there, what we find here is that the vegetations have been very uniquely identified into two information categories. One is a category which has a much darker tone, while the other has a mid gray tone which is available. Through the histogram, we can make an assessment as to which portion actually belongs to the vegetation and which portion belongs to the non-vegetative areas, as there is a very single and discrete definition of the separation between the information as can be seen from the histogram. Well, this type of information is good when one wants to extract single class information from multispectral data sets. The next indices is the normalized ratio vegetation indices, or in short known as NRVI. Well, Barrett and Guer in 1991 proposed a modification to RVI, whereby the results of RVI 1 is normalized over RVI plus 1. This normalization is similar in effect to the NDVI, that is, it reduces the topographic illumination and the topographic effects, and it creates a statistically desirable distribution. This particular slide shows the NRVI. Since NRVI is the reverse of NDVI, what we find is that water bodies and moist soil areas are appearing in brighter tone, whereas all forest or vegetation indices or agricultural areas are now being shown in darker or mid grade tone color. In this particular case, we see that the information is towards the higher side of the brightness scale. The next indices to be studied is soil adjusted vegetation indices, or in short called as the SARVI. SARVI, as a matter of fact, introduces a soil calibration factor L to the NDVI equation in order to minimize soil background influences resulting from first order plant spectral interaction. SARVI can be represented as follows. It is 1 plus L multiplied by the difference of NRI minus the red band divided by NRI plus the red band plus I, and value of 0.5 is assigned to L in the reflectance space, and it was found to minimize the soil brightness variations and eliminate the need for additional calibration for different types of soils. The utility of SARVI for minimizing the soil noise inherent in the NDVI has been incorporated in several studies. Here we see the SAVI image. It is more or less similar to NDVI, except that in the exposed areas where there is soil, the information has now been converted into black color or black tones, since the impact of soil has now been taken out from the pixel representing the vegetation information. The next indices which is there is atmospherically resistant vegetation indices. Up till now, the indices that we have discussed, they have considered the topographic effect and the contribution of the soil background, which is to be abstracted from the pixel information containing vegetation. Kai in 1995 developed a modified SARVI called MSARVI that uses an iterative continuous L function to optimize soil adjustment and increase the dynamic range of SARVI. SARVI was made less sensitive to atmospheric effects by normalizing the radiance in the blue band, red band and the near infrared bands. Well, this indices is what we call it as ARVI, or atmospherically resistant vegetation indices, and it is represented by the equation wherein we take the difference between the near infrared minus the reflectance contribution coming from the red and the blue, where the red and the blue contribution can be expressed by the equation P RB is equal to P red, that is the red band, minus gamma, a factor, multiplied by the difference between the blue reflectance minus the red reflectance. This last portion of the equation is the correction factor for the atmospheric effect. The technique requires prior correction for molecular scattering and ozone absorption of the blue, red and near infrared remote sensor, and hence the term P star has been used. ARVI uses the differences in the radiances between the blue channel and the red channel to correct the radiance in the red channel and thus reduces the atmospheric effects. Unless the aerosol model is known a priori, gamma is normally equal to -1 to minimize atmospheric effects. Kaufman and Tannery in 1992 provided guidelines where different values of gamma have been suggested for different environmental conditions such as continental, maritime, desert or the Sahel area or heavily vegetated areas. For a value where the gamma is equal to 1, the value of ARVI is nearly 4 times less dependent on the atmospheric effects of NDVI. For maritime atmosphere, the improvement is only by a factor of 2. For continental aerosol, the improvement is by more than a factor of 4. Again, the improvement of the resistance of the ARVI to atmospheric effects is much greater for vegetative areas or regions than over arid regions. This particular image now shows the information as obtained after applying ARVI transformation. What we find is that the information tends to be clustered at the lower region of the histogram, and thereby the information is being represented by midtones of gray. The next indices is an improvement of over ARVI. In ARVI, we have considered the atmospheric effects. However, we have not taken into consideration the soil. Hence, Hewitt and Lewis in 1994 integrated the L function from SARVI and the blue band normalization in ARVI to derive a soil atmospherically resistant vegetation indices, in short SARVI, which corrects both soil and atmospheric noise as would a modified SARVI, or what we call it as modified SARVI. So, SARVI can be represented as the difference between the NIR and the difference between the red and the blue information divided by NIR plus reflectance of the difference between the blue and the red plus the soil correction factor L. In this particular slide, we now see the SARVI image, which has been now represented here. Interestingly, in this particular image, what we do find here is that there in the mountainous regions where there are valleys, the information is distinctly brighter in comparison to those forested areas where the cover is more uniform. The information can be again seen to be clustered around the lower end of the brightness scale, with a very distinct boundary being shown at the end of the histogram, which separates a very small region of a water body which can be seen in the central part of the river, which has now been shown as a silver band or a loop. This is primarily because that this is a stagnant water and the river is carrying lot of sediments, and the sediments have played a major role in enhancing the reflectance, and since this has been abstracted, the characteristics of the water has been represented by a very distinct tone in the image. SARVI that we have, and it is represented by the equation which is given here as 2 PNIR plus 1 under root NIR plus 1 whole squared minus gamma multiplied by the difference of NIR minus the difference of red and blue reflectance divided by 2. This is it is nothing but the solution that we get by taking the modification to SARVI. And now we see the SARVI image which is there, and this particular image, as a matter of fact, is totally different from all the vegetation indices images that we have seen up till now. What we find here is that the topographic informations again have been very explicitly highlighted, and it appears as if we can now identify the micro channels within the mountainous regions, whereas when these streams, when they reach on to the plains carrying lot of sediment, they are depicted in white, whereas one of the major rivers which is flowing through this particular region, all the water carrying channels are seen in black color or black tone, while the abandoned channels or dry channels of the river, they appear to be in white or brighter tones. This is a very distinct information, whereby we have now looked at how the effect of atmosphere and soil background affects vegetation informations. A sensitive analysis on the original NDVI and the improved vegetation indices such as SARVI, ARVI, SARVI and MSARVI was performed, and it was concluded that if there is a partial atmospheric correction to remove relics and ozone components, then the best vegetation indices would be SARVI and MSARVI, with NDVI and ARVI being the worst. And if there is a total atmospheric correction, then there would be mainly soil noise, and the SARVI and MSARVI would be the best equation to use, and NDVI and ARVI would be the worst. If there were no atmospheric correction at all, that is no relics, no aerosol or no ozone correction, then SARVI would become slightly worse, but still would be the least overall noise. The NDVI and ARVI would have the most noise and error. This, as a matter of fact, now provides an input to the scientists and researchers regarding which indices to be used and at what would be the advantage which could be derived. The Modest Land Discipline Group recently proposed another indices which is known as the Enhanced Vegetation Index or EVI to be used with Modest data sets. They gave the relationship as EVI is equal to NIR minus the red reflectance multiplied by 1 plus L, which is the soil adjustment factor, divided by the NIR plus constant C1 multiplied by the red reflectance minus constant C2 multiplied by the blue reflectance plus the soil correction factor L. The EVI is a modified NDVI with a soil adjustment factor L and two coefficients C1 and C2, which best describe the use of the blue bands in the correction of the red band for atmospheric aerosol scattering. The coefficients of C1, C2 and L are empirically determined to be 6.0, 7.5 and 1.0 respectively. This algorithm has improved sensitivity to high biomass regions and improved vegetation monitoring through a decoupling of the canopy background signal and a reduction in the atmospheric influences. Now, let us look at some of the other vegetation indices which have been developed for very specific studies. First is the weighted difference vegetation indices, or in short WDVI. This has been attributed to Richardson and Wiegand and Clevers, Kerr and Pichon, and it is expressed as the difference between the NIR and the red weighted by a factor gamma. Although simple, WDVI is as efficient as the most soil based vegetation indices. The effect of weighting the red band with the slope of the soil line is the maximization of the vegetation signal in the near infrared band and the minimization of the effect of the soil brightness. In this particular image, we can see the information as depicted through WDVI, and what we can see is that the information of the soil has been minimized and these are appearing in black color, whereas vegetation informations are appearing in much brighter gray tones. Another indices which is known as the infrared indices, or in short called as II, was developed by Hardesky and his group of investigators in 1983, wherein they took the NIR band of the thematic mapper and took its difference from the middle infrared region, that was the TM5 band, and took its division and with the sum of the two bands it was found that this is more sensitive to changes in plant biomass and water stress than NDVI for wetland studies. Here we can see the IIR image which has been generated, and what we can find here is that the information of the vegetation in terms of its stresses can be seen very clearly. Wherever there is a stress, this is seen very clearly in the agricultural domains. The histogram depicts two broad regions of information very distinctly separated by a very small gap. However, this type of separation was not available in any other type of vegetation indices that we have discussed up till now. Another indices which was also identified, and that was moisture stress indices. This was developed by Rock et al. In 1986, wherein it is a ratio of the TM5 to the TM4 data set. It is, and what we find here is that in this particular case the soil information gets enhanced in comparison to the other informations which is there. The histogram also depicts two distinct groups of information clusters, and this can be utilized by the analyst when separating soil from vegetation informations. The next index is the middle IR index developed by Music and Petlier in 1988, wherein they found that a strong correlation with the middle infrared index and soil moisture exists. Thus, they took a ratio of the TM5 to TM7. Over the period of time, it was found that NDVI based products can be unstable with varying soil color and soil moisture conditions and atmospheric conditions. MIR index, as a matter of fact, tries to cater to these anomalies which may exist. Here we see the MIR index image, and what we can see is that in the vegetation domains, there is a distinct level of information representation, wherein the gaps in the soil within the forest regions or heavy vegetation regions have been very clearly highlighted, and can be thus the image appears to have lot of pock marks, that is, there are appearing to be small holes, thereby giving as if there are certain depressions in the image. Similarly, the streams within the forested regions are also getting highlighted very distinctly in this particular image. Thus, there is a need to have a NDVI related product which is globally accurate, does not require calibration, and yet remains constant under changing atmospheric and soil background conditions. Thus, a series of improved indices which incorporate a soil adjustment factor and also a blue band for atmospheric normalization. Now, we come to the next group of vegetation indices, and this is what we call it as the distance based vegetation indices. Well, this group of vegetation indices is derived from the perpendicular vegetation indices. The main objective of this vegetation indices is to cancel the effect of the soil brightness where vegetation is sparse or pixel contain mixture of green vegetation and soil background. This is particularly important in arid and semi-arid environments. The procedure is based on the soil line concept as outlined earlier. The soil line represents a description of the typical signatures of the soil in a red near infrared bispectral plot. It is obtained through linear regressions of the near infrared band against the red band for a sample of bare soil pixels. Pixels falling near the soil lines are assumed to be soil, while those further away are assumed to be vegetation. Distance based VIs using the soil line require the slope B and the intercept A of this line as inputs to the calculation. Unfortunately, there has been a remarkable inconsistency in the logic with which this soil line has been developed for specific vegetation indices. One group requires the red band as the independent variable and the other requires the near infrared band as the independent variable for regression. However, it is found that soil and vegetation tends to provide more mixed information due to varying cover, and hence the perpendicular vegetation indices as proposed by Richards and Weekend has been developed, and this is an index of measure of plant development and soil background. A plot of the red band on the x axis and the infrared band on the y axis shows the bare pixels lie along a line known as the soil line at an angle of 45 degrees to the respective axes, where all vegetation points lies perpendicular and left of it. Larger the distance of the soil line, it is an indication of the greater amount of vegetation present. Further, if a point lies on the soil line, then the position of the point on the line is an indication of the soil moisture of the soil. If this point is on the lower side of the line, it indicates greater amount of moisture content. PVI was initially developed for Landsat MSS sensors and has been expressed as follows. PVI 7, which takes the relationship between MSS 7 and MSS 5, and it has been expressed as under root of 0.355 multiplied by MSS brightness values minus 0.149 multiplied by MSS 5 brightness values whole square of this plus 0.355 MSS 5 brightness value minus 0.852 multiplied by MSS 7 brightness value whole square of the same. Another indices which is called as PVI 6, which uses the MSS 6 band along with MSS 5. MSS 6 as a matter of fact is a good indicator of the rock content. So, two indices have been proposed, and now let us look at the two images which can be derived from the two relationships which is here. So, what we find here is in PVI 1, which is nothing but PVI 7, this is showing the information which is very similar to what we have seen in SARVI. The information here is very unique, such that the soil background have been very uniquely masked out from the data sets. When we go on to PVIs, since this is an indicator of the rock presence, the area does not contain too much of information regarding the rock exposure, and hence what we can understand from this image is that bare soil in this particular case has been masked out very effectively in comparison to what had been seen in PVI 1. With this, I conclude my first part on image transformations. In my next session, I would focus on the different types of orthogonal transformations and some of these special indices developed for specific applications other than vegetation. Thank you.